but I'll do my best. Yeah, I'm Moritz. I'll be talking about two frameworks that I developed with my co-authors, SoMo and SoMo Gym. And both of these frameworks, in developing them, we were operating under the assumption that many questions regarding the design and control of soft robots can be answered with simulations that do not have the accuracy that we see in FAA methods or, for example, Elastica. So we're going to even more simple representations of soft robots than assuming custard rods. And we built these tools for applications where a high-level understanding of the dynamics of soft robots is sufficient to better solve the task at hand. In those settings, we assume that we can approximate the soft arms and soft fingers as a chain of rigid links, so very simple. We do believe that this assumption holds for applications ranging from planning robot-to-robot interactions with multiple agents and contact interactions between soft robots and complex environments, if we look at the right level of granularity. Common examples would be whole arm grasping with an elephant trunk manipulator, steering a soft arm through clutter, debris or air ducts, and in-hand manipulation with soft fingers. This stark simplification, I would say, allows us to build much faster simulations, which is very helpful if you want to do reinforcement learning or design optimizations for continuum manipulators, where we really do need to run a lot of rollouts of whatever task we're simulating to get any good results. So let me first briefly introduce the SoMo framework. SoMo is just a very thin wraparound PyBullet that uses a standardized format to define, control, and simulate continuum manipulators. This means that a user can simply specify key features of a continuum manipulator in a YAML file, and then SoMo builds a URDF from this description and loads it into PyBullet as a SoMo continuum manipulator object. Several of these objects can be simulated at once and can each be controlled with a simple command, so it makes it fairly easy to build worlds with soft continuum manipulator in them. As I mentioned earlier, each of the SoMo manipulators consists of a series of rigid links connected with spring-loaded joints that can be given a specific stiffness or damping. A manipulator can have several independently addressable actuators, of course, and each of these actuators can be passive or actively controlled. The user, when specifying their YAML file, can pick from a number of link shapes. You see a few of those on the right here. For example, we can use spheres, a cube or a cylinder, capsules, and like this stadium type shape to connect them to get their continuum manipulator. The number of links can also be varied, which allows us to programmatically switch between different levels of granularity, which means different levels of accuracy and different levels of precision. Yeah, and then we can also vary the number of joints, of course, and the contact properties that we prescribe. I see I skipped some. Oh well. Anyway, so I'm just going to show a few examples from projects from our lab that use SoMo simulations for actuation and design studies. On the upper left here, you see a four-fingered hand rotating a cube, both in hardware and in simulation. And here, each of the fingers is approximated by 20 segments, but the behaviors match the hardware quite well. On the top right, you see a hand with a different finger arrangement, and this hand is manipulating a box. And in this work, we used SoMo to evaluate several hand designs that vary in the finger arrangement to see what the pros and cons are of each of the designs for different object shapes with different aspect ratios. On the bottom left, you see a large continuum arm picking up and dunking a basketball, really just to highlight how easy it is to build custom environments in SoMo, thanks to how we leverage Bullet as the underlying physics engine. And then finally on the bottom right, you see a design study where we optimized for pinch grasping with soft fingers. So what we did here is that we varied each of these fingers consists of two independently controlled actuators, and we vary the length ratio between them to optimize for pinch grasping over a range of objects with varying sizes, and also verified the results that we got in hardware experiments. I'll now switch over to SoMo Gym. SoMo Gym is a toolkit that facilitates the development and evaluation of controllers and reinforcement learning algorithms for soft robots, and it uses SoMo under the hood. At the core of SoMo Gym, we have a collection of simulated tasks that involve various types of soft robots. These robots include snake-like robots, as shown on the left here, soft arms, and various hands and grippers. Each of these tasks is implemented in a simulation environment that follows the interface and structure introduced by OpenAI's Gym. So that means that we can easily integrate SoMo Gym environments with common reinforcement learning frameworks like stable baselines, and really we have an interface that is very familiar to everyone. And now let's take a look at some of the tasks that are implemented in SoMo Gym. On the left here, you see a soft arm that is asked to move an orange cube to the green goal position. And yeah, as you'll notice, a lot of these tasks will focus on somewhat manipulation type tasks because that's really what we're interested in our lab. And in the middle, you see a soft arm that aims to move its tip towards a target in the presence of an obstacle. Of course, we can also have multiple obstacles. And we also see here that we're bracing against the obstacle to get to the ideal position. And then on the left, on the right, we see an anthropomorphic soft-fingered hand that aims to reorient a pen such that the pen aligns with the desired pose. The pen is shown in blue and the target pose in green. And you see here how these 5 fingers rotate the pen slowly to where we want it to be. And some additional SoMo Gym benchmark tasks shown here. On the left, you see a snake-like robot that's tasked to move to a green target position, and this uses anisotropic friction to have like a slithering-like locomotion. And then in the center, you see a 4-fingered hand that is rewarded for rotating the green cube around the z-axis, so one of our element manipulation tasks. And on the right, you see an antipodal gripper that is rewarded for picking up a cube. The cube is connected to the ground with a virtual spring, meaning that a larger achieved cube height corresponds to stronger grasps, which makes it easy to put together a meaningful reward formulation when we use this task for reinforcement learning. And then as part of the SoMo Gym benchmark suite, we specify the details for each of these tasks, like the observations and reward formulation, and set what they are as part of the benchmark, but they can also be easily adjusted through configuration files. So we can change what the exact observation space is. So when we look at the manipulators, and for the default configurations, those make up a benchmark suite of soft tasks that can be used to evaluate controllers and reinforcement learning algorithms. And for this default benchmark, we trained policies for all of these tasks with 3 common RL algorithms: proximal policy optimization, soft actor critic, and twin delayed deep deterministic policy gradient. And I'm now going to show some of the benchmark results that we got for these tasks. First, here you can see the training history and the result from executing the final policies for a soft arm that navigates its tip to a target position. And as you can see, PPO and soft actor critic do well across all 3 seeds. With some variation in policies that were obtained. And a bit more interesting here is the task where we move around the block to a target position. And we see videos of select policies executed at the bottom, and again, PPO and soft actor critic are doing fairly well. TF3 not so much. And really some of the most exciting policies that we saw, I think, emerged when we trained on the in-hand manipulation task, where the robot is rewarded for rotating this green cube. In the soft actor critic, for example, in the middle here, we found a policy in which the cube is spun around in a pretty dynamic way. I'm going to replay this quickly. So, and I think this really showcases the use that SoMo and SoMo Gym can have with making it really easy to build these environments and fast simulations, because we're not very accurate. We're not achieving the accuracy that most other tools have, but we believe that's not always necessary. If we reason over these inner manipulation tasks, I think we want to explore different types of policies at a very high level, where the high level dynamics are very important. And then eventually we can go to a more fine-grained simulation. And here is another slight variation of the in-hand manipulation task that I showed earlier. This is what we call inverted in-hand manipulation task. And in this setting, the cube that is to be rotated is placed on a table and therefore cannot fall off, which makes this task much easier. And cool policy I would like to point to here in the middle with a soft actor critic is that we see emergence of kind of this finger gating behavior. So yeah, I think that's kind of cool. Finally, here you see the benchmark baseline for snake locomotion, and only in this task, only soft actor critic found a policy that does well. The other algorithms did not find policies that improve on just not taking any actions, and this is slowly getting started. It does clearly not look as smooth as an actual snake, but we do see this typical slithering motion that leverages the anisotropic friction. So, and then some weird other behaviors. And so finally, we set out to demonstrate that these abstractions are indeed useful, and that the policies that we develop can be transferred to real hardware, despite the stark simplifications that we make. And we did that by executing a policy trained exclusively in simulation on our hardware platform. And I'm playing this now here. And as you can see, it works reasonably well. And the current work is that we're working on transferring some of the more dynamic, aggressive policies to hardware. Yeah, and then I would like to end my presentation with a big thank you to all the great collaborators that I had working on this, chiefly among them Clark, Thibault, Tom, McCarthy, and Rob. And also thanks to the organizers for putting this together. I think it's a really exciting series of talks, and I guess I'm giving you guys some time back since I don't have as many amazing videos yet as Elastic can. And happy to hear questions or discussions.
Cool. Sweet. Well, thank you so much, Moritz. I greatly appreciate the time back. Yeah, and super cool work. Are there any questions either from the in-person audience or on Teams? I can't read the chat, so please just unmute and speak out your question.
I have a question.
Oh, go for it.
Go on. Hi, thank you for this talk. I was wondering, in comparison to maybe something like we saw with Pielastica, what would the prospects be like for doing more complicated either sheets or bulk volumetric type of simulations using the SoMo framework?
Yeah, I think it's a great question, and I would, to be honest, I think SoMo would not be the right tools. We think SoMo and SoMo Gym have a very specific place within the simulation for soft robots kind of space, and more complex behavior is not, or like volumetric deformations is not what we're trying to do. And I would say there are many better tools presented here for that. I think what SoMo and SoMo Gym can be useful for is getting like a high level understanding and intuition that can then guide higher accuracy simulations in the future. So for example, I think we can roughly reason about how we manipulate this cube, right, with this simple approximation, but then how the fingers make contact exactly and all of these things we can't do. But can maybe be also a way that we interface with more detailed simulations for like getting, because for example, it's often we have, because of the compliance of the soft robots, we often only, if we want to plan how an arm moves through clutter, we don't need exact resolution of how the contact is happening at each object. We just roughly need to know how we can go through the clutter.
Cool. And then Mathieu, did you have a question?
Yes. So, well, thanks. I really like the talk. So I have a question about from a control perspective of your manipulator with the 4 fingers. How do you manage the coordination among the fingers? It's like, do you do an end-to-end, solve, or what? How do you do?
Yeah. So what you saw. In the learned policies, each finger is controlled independently, and we learn end-to-end. We observe the state of the finger, which is the manipulator position, and the cube. So the state of the environment is the observation, so cube orientation and position, and then we learn an end-to-end policy that does not make any assumptions about mirroring fingers, for example. So that's why we have these like uneven fingers. So it's all learned end-to-end, which is, I think the fact that we can iterate very quickly helps for that.
Yeah, of course. So basically, if I understand, you have the state of the environment, and then the state of each finger is part of a big input array that you pass to your network for the training?
Yeah, exactly.
All right. Okay. Thank you.